Hello, my name is Dikhale, and I will be presenting a paper titled Hierarchical Graph Neural Networks for Proprioceptive 60-Pose Estimation of In-Hand Objects, co-authored by Alireza Rezazadeh, Soshi, and Naveed Jamali. This research was conducted at Honda Research Institute, USA. What problem are we trying to solve? In-hand object manipulation tasks often require an accurate estimate of the object's 6D pose. To achieve this, state-of-the-art approaches in 6D pose estimation utilize observational data from one or more modalities, such as RGB images, depth, and tactile readings. How did we approach this problem? We combined vision and touch data with geometric information using a hierarchical graph neural network architecture. To facilitate multimodal information flow, we introduced a novel hierarchical message passing operation. Additionally, we leveraged proprioceptive information, including tactile sensor position data, along with vision and touch data. Our network architecture consists of three main blocks: an encoder, a processor, and a decoder. The encoder maps the observation from vision, which consists of RGB and depth point cloud, and tactile, which consists of a contact point cloud, to a multimodal graph representation while accounting for the proprioceptive information from the hand. The processor performs multiple rounds of hierarchical intramodality and intermodality message passing to update the graph. The decoder extracts a readout from the updated graph and estimates the object's 6D pose. For our evaluation, we compare the performance of our network with two state-of-the-art baselines: VITA, a visuotactile 6D pose estimation algorithm by Dikhale et al., and PointGNN, a graph-based object detection method by Shi et al., repurposed as a graph-based 6D pose estimation baseline. We trained our networks as well as the baseline on a synthetic domain randomized dataset comprising of 11 YCB objects, as proposed by Dikhale et al. To evaluate our network's performance, we conducted a quantitative analysis by measuring the position and angular error of the pose estimates and comparing them to both baselines. Our approach consistently outperformed the baselines on both position and angular error metrics for all objects in the dataset. In our evaluation, we observed that as we increased the occlusion level, our model outperformed both baselines with statistical significance on position and angular error metrics. This suggests that our model is more robust to reduced visual information. We deployed our network on a real hardware setup and performed qualitative analysis. Our hardware deployment setup consists of an Intel RealSense camera and an electro hand instrumented with Zila tactile sensors attached to a Sawyer robot. The performance of our network and the baseline network VITA under varied visual input. Our network's performance is shown in the top left corner, while the baseline network VITA's performance is displayed in the bottom left corner of the video. Both networks were trained solely on a synthetic dataset, and during deployment, they received the same input. Notably, our approach shows better robustness to occlusion compared to the baseline. This can be observed from the plot in the bottom right corner, which displays the live angular and position error with respect to the ground truth pose, obtained using a motion capture system. We evaluate the performance of our network and the baseline network under varied tactile information by changing the fingers in contact with the object. Our results show that our network outperforms the baseline by maintaining its pose estimate while the baseline becomes unstable. Even in this condition, where visual information is limited and tactile data varies, our network maintains a decent pose estimate with an angular error of around 10 degrees and position error of 1 centimeter, as shown in the angular and position error plots on the bottom left corner. We evaluate the performance of our network and the baseline network on two other YCB objects, the cracker box and the sugar box. In conclusion, we proposed a graph-based framework for estimating the 6D pose of in-hand objects based on vision and touch observations and accounting for proprioceptive information. We introduced a novel hierarchical approach for learning a graph-based representation of the observational data on two modality levels using hierarchical message passing operation that allows the information to flow within and across modalities. We showed that our approach accurately estimates the object's pose and is robust to heavy occlusions. We deployed our model on a real robot and showed successful transfer to pose estimation in the real settings.